Welcome back to the series of lectures on high-performance scientific computing. In the last video, we had seen how to use MPI along with CUDA. We had used this to look at two specific problems. One was for Monte Carlo integration and the other one was trapezoidal rule integration. We will just revise what Monte Carlo integration is. So here we use a random sampling to approximate an integral, and then we generate n random points in the region of integration. If the function values at each of those points is greater than the point that we have generated, then we say that the point is within the integral region, otherwise it's outside. We sum up the total number of points and then we look at the area that could be there, which comes out as a ratio. So now this works well for high dimensional problems, and we have implemented this specifically to calculate the value of pi by integrating the curve of a quarter circle. Let us now see how this is being implemented with MPI and OpenACC. Remember, OpenACC is a directive-based programming approach which makes our life very easy in the sense that we do not have to handle explicit copying of memories back and forth. So we will now go and see how this is being implemented in an OpenACC code. So here you can see this is the MPI plus OpenACC integration implementation of the Monte Carlo numerical integration. The function that we are going to integrate is f of x 4 over 1 plus x square over the interval 0 to 1, which approximates the value of pi. So what are we doing over here? We are including the standard MPI libraries, the standard input-output libraries. We are now including the OpenACC libraries as well, because we're going to do OpenACC. And then we write a very simple, first we look at it as a very simple serial program, right? And then we look at it from an MPI perspective. Here we start with the main, and here we are going to have obviously the MPI initialization of the entire environment, where we take in from the command line what the inputs of total number of processors, etc. are. We then find out what the rank is using the MPI com rank function. We then store it in the variable rank. We then look at what is the size of the MPI communication world, and we put it in the variable size. We have hard-coded the number of samples above to about 10 million. And we are saying the samples per process is number of samples divided by the size. So after this, we have a barrier. This is when we start the timing function, and this is where we would actually, in case if it was a straight serial code in the sense which is not being accelerated on a device, just being run on the CPU, we would loop through all the sample points, compute the random x and y, and then count it if it lies within that region or if it does not lie within that region. So in this case, what we are doing is that we are now doing a hash pragma ACC parallel loop region, and we are doing a reduction over the local count. So essentially what's going to happen is the compiler is going to sort of offload this for loop onto the device and then do the computation the way it needs to be done. Finally, once we have computed the local count, we are then going to reduce it to the total count, because remember, each MPI process will have its own value of local count because it will have its own series of random numbers, and it will compute its it will reduce its local count into the total count using the MPI reduce function. This will be done on rank 0. And then we end the time counter, and if the rank is equal to 0, then we estimate, we put out the estimate for the value of pi by just calculating what the number of samples are within the curve to be integrated divided by the total number of samples. So that ratio will give us the area. So we then estimate pi, and then we put out what the execution time is, and then finally we finalize and run. So you can see that the MPI code, which is just a pure MPI code, now becomes an MPI plus GPU code with a very simple inclusion of just one line, which is the hash pragma ACC parallel loop. Now, if we want to change this code to be just a pure MPI code without having any, device acceleration, then we have two options. Either we can just delete this directive over here, or we can choose to keep it in but just not pass the flag FOpenACC while compiling. So we'll now see how to compile this particular code. So we can just say MPI CC minus FOpenACC, which basically tells me please recognize the OpenACC directives, Monte Carlo MPI OpenACC.c. So you can see both the compilation process and the code writing process is far simpler if you use OpenACC compared to CUDA. And now we just have a direct executable, which is a.out, which has now been created and is ready to run. We did not have to go through the multiple steps like we had to do with MPI and CUDA, where you had to compile the CUDA code, create an object file, and then finally link the object file with all the relevant libraries. Here MPI-CC recognizes all this, and the moment you give the FOpenACC flag, it also recognizes the underlying compiler recognizes that that bit of code or that implicit for loop now needs to be offloaded to whatever accelerator you have, and then it will write the appropriate device code for it and send it off to the accelerator. Let's now see how we execute this code. Say MPI run, whatever number of processes you want to give, and there you get an answer. If you notice here, we are also getting the same answers, but we are getting with slightly different times. If we change the number of processors, we get a slightly different answer, and we get slightly different timings. You have noticed in the previous example and also in this example actually that the timings sort of vary a little bit. In the previous example, you would have noticed in the previous video that the times actually kept on increasing a lot. That's because we had hard-coded the CUDA code and there was a lot of overhead in doing all the CUDA mem copies, etc. Here the compiler is doing a far more efficient job of doing things when we pass the OpenACC flag. So actually when you increase the number of processors, you're actually seeing a decrease in time. And this will only happen to a certain amount of number of processors, beyond which again then you'll see an increase in the the timing, and you will see no benefit in the speed up, because all the overheads of creating and offloading, of sending data back and from the host to the device and device to the host will all catch up eventually. So this is how we accelerated the code for Monte Carlo integration very quickly by just using an OpenACC directive. If you want to now go back to a pure MPI implementation and just do not want any acceleration on the graphics card, we just simply have to just remove this flag of FOpenACC, and now this has been compiled to run purely on a CPU version, and we can again run this code and see what the answers come out to be. And because this problem is a fairly small problem, the difference in time between the CPU execution and the GPU execution is not too much. Now, let us go back and look at the same problem with the trapezoidal rule for numerical integration. Here again, we are approximating the integral by dividing the area under the curve into several trapezoids. We then compute the functional value at the subinterval endpoints. We then sum the area of the trapezoids and then put it. This is more a deterministic way of doing the calculation rather than doing it in the way of how we have done it with the Monte Carlo method, where we used random numbers. So again, we go back and we now see what the code for the trapezoidal rule looks like. So here again we have defined the function 4 by 1 plus x square, which is a function to integrate, and then we are now having the main function where we give the rank, the size, and the total number of trapezoids. We initialize the MPI function, then we put the variable, or the personal variable of the rank into what has been declared. We then find out what the MPI communication size world is, and then we put it into the variable size. We then divide the interval among the different processes. So each MPI process again will get its own chunk. It will have its own local starting point of A and B, which are the local, the lower and the upper limits of integration. And then once each of the MPI process based on its rank has computed what area it needs to integrate, you then put the MPI barrier to start the timing. And then for the local result for that each MPI process, you call the function trapezoidal rule, which passes the lower limit, the upper limit, and the total number of trapezoids locally it's going to integrate. Once the local results are done, we then do the reduction from the local results to the total results, and this is being done on rank 0, where it is being summed up. Then you have an MPI barrier, then we end the clock over here, and then finally rank 0 will put out what the estimated integral is and what the execution time is. So now let's look at the trapezoidal rule function, which is actually kind of doing the compute, because that's what is actually computing the local area. So here we are saying that hash pragma ACC data copy sum. So what we are essentially saying is that please copy the initialized value 0 from the host to the device over here. So the device now has a value sum correctly, and it's initialized to 0. And then we are doing an ACC parallel loop with a reduction operation on the variable sum, where each point is going and being computed, and then we then put it up into this f of x, and then finally we get the f of x to be over here, and this value is then returned. So each local result is then returned for each of the MPI processes. So this way we are now able to compute the numerical integration for 4 by 1 plus x square, which is essentially approximating the value of pi. We will now see how to compile this. We again say MPI-CC minus F OpenACC because we want to accelerate this on the accelerator. We give it the source file, and in this case I don't want it to go to a.out, so I will now say put it into executable called trap MPI OpenACC. So this will now create this, and you will notice that when I do with OpenACC, we have one step less. We do not create a separate object file. We go directly from the source code to creating the executable. So now the executable for trap MPI OpenACC is ready. We can now go ahead and execute it. We can say MPI run. Minus NP, we can give it the number of processes. In this case, let me put 6. Trap OpenACC, and then we calculate the value of pi. So you can see that for every case, we are getting about some reasonable answers for the value of pi. So in the last 2 videos, we have seen 2 different types of implementation of using distributed memory machines and accelerator hardware in conjunction. We can take an existing MPI code and accelerate it even further on a device, either by writing CUDA kernels for it and linking those CUDA kernels to your MPI program, or the other way to go about doing it is to use OpenACC directives inside your MPI program. In both these techniques, we are able to harness the power of GPUs over a distributed machine. In modern day computers, that is how most systems are. You will typically have hundreds of nodes. Each node will have its own individual accelerator. So you will not only have to do distributed memory programming, but you will also have to accelerate it on these accelerator cards using either CUDA if it is NVIDIA accelerators, or you can use OpenACC for any generic accelerators to be a little bit agnostic. And that's the way you can get maximum efficiency and maximum scaling of your codes. Thank you.